Okay, I start with 53. The unit Henry is equivalent to what? Is equivalent to volt times second divided by ampere, Vs divided by A. And therefore here the diagram shows an indicator that is part of a circuit. The direction of the EMF induced in the inductor is indicated. Which of the following is possible? D is possible. The current is increased and leftward. Left ke ka mo side in the opposite the E direction. Current by increaser and then is leftward. So a 1010 ideal solenoid has an inductance of 3.5 millihenry. So when the solenoid carries a current of 2.0 amperes, the magnetic flux through each turn is what? Is C, which is 7.0 times 10 to the power negative 4. That one I will always choose, and therefore a 1010 solenoid has an inductance of 4.0 millihertz. To generate an EMF of 2.0 volts, the current should change at a rate of E of 500 amperes per second. So a long amperes per second. So a long narrow solenoid has a length of L and a total of N turns. So each of which has cross-sectional area A. So its inductance is B. What is B? B, we have mu O, we have N squared, we have A divided by length. Mn, and therefore micro N mna divided by mna squared, therefore divided by L. And therefore a fluid coil of wire having 5 turns has an inductance L. The inductance of similar coil having 20 turns is what? Is C, 16L. 16L, and therefore we have an inductance L, resistance R, an ideal battery of EMF E, wire and series. So a switch in the circuit is closed at time t is equal to 0, at which time the current is 0. At any later time t, the current I is given by what? E, which are E divided by R, and therefore you multiply that by 1 minus E to the power of negative RT divided by L. An inductance L, resistance R, an ideal battery of EMF E are wired in series. So a switch in the circuit is closed at time t is equal to 0. At what time the current is 0? At any time later t, now they are looking for the EMF, they are not looking for the current. The EMF of the inductor is given by what? By D. D, it's small e to the power of negative RT divided by L. An inductance L, resistance R, and an ideal battery of EMF E are wired in series. So a switch in the circuit is closed at time t is equal to 0, at which the current is 0. So at later time t, the potential difference across the resistor is given by what? By E, which is E, and therefore you open brackets is 1 minus E to the power of negative RT divided by L. Therefore an inductance L, which is resistance R, an ideal battery of EMF E are wired in series. So a switch in the circuit is closed at time t is equal to 0, and therefore at which time the current is 0. At any later time, the potential difference across the resistor is given by what? By E. Yeah, I did that one. An 8,0 millihenry inductor and a 2,0 Henry are wired in series to an ideal battery. So a switch in the circuit at close time t is equals to 0. At what time the current is 0? The current reaches half its final value at time what? At A. Bobunale 28 milliseconds. And then they repeat the same question again. But now what's the difference between that question and this question? After a long time, like time was 28 years. Now they want current. Current now is going to be B. 10 amperes, 10 amperes, 10 amperes. It's a repeating thing, repeating shit. So an 8 millihenry inductor and a 2,0 ohm resistor are wired in series to a 20-volt ideal battery. So a switch in the circuit is closed at time t is equal to 0. At what time the current is 0? After a long time, the current in the resistor and the current in the inductor are what? Would be 10. Okay, we have the same question now. This question has been repeated 3 times. The first one they're looking for time is 28, and then the second one they're looking for current is 10. And therefore now they're looking for what? For potential difference. Potential difference 200. Bobin Gilan said 200. Now it's different now. An inductor with inductance L, resistor with resistance R. Resistors and a resistor R are wired in series to an ideal battery with EMF E. A switch in the circuit is closed at time t is equal to 0. At which time the current is 0? A long time after the switch is thrown, the potential difference across the inductor and resistor is A. It's 0. It's 0E. OE Wafana. If both the resistance and the inductance in an LR series resistor circuit are doubled, the new inductance time constant will be E, unchanged. It's unchanged. When the switch S and the circuit shown is closed, the time constant for growth of current in R2 is what? Is B. B is L over R2. L over R2. So the diagrams show like 3 circuits with identical batteries, identical inductors, and identical resistors. So you should rank them according to the current through the battery. Just after like the switch is closed from least to greatest. So the answer is going to be C. 1, 3, 2. So you choose the ones on the side and therefore followed by the middle one. An inductor with inductance L, resistor with resistance R are wired in series to an ideal pattern with EMF battery with EMF E. A switch in the circuit is closed at time 0, and therefore at which time the current is 0. A long time after the switch, the potential difference across the inductor and resistor is what? It's A. It's 0 and E. If both the resistance and the inductance in an LR series circuit are doubled, the new inductance time constant will be E, unchanged. When the switch in the circuit shown is closed, the time constant for the growth of a current in R2 is what? Is B. L over R2, which are L here, y divided by R2. Therefore, the diagrams show 3 circuits with identical batteries, identical inductors, and identical resistors. Rank them according to the current through the battery just after the switch is closed, from least to greatest. So the answer is C. 1, 3, 2. Okay, I did this one. 69. Immediately after switch S in the circuit is closed, the current through the battery is what? It's D. VO divided by R1 plus R2. But it makes sense. VO divided R1 plus R2. Roll 70 now. We are finishing. A 3.5 millihenry inductor and a 4.5 millihenry inductor are connected in series. So the equivalent inductance is what? Is E, which is 8.0 millihenry. So a 3.5 inductor and a 4.5 millihenry inductor are connected in series, and a time varying current is established in them. So when the total EMF of the combination is what? 16 volts. The EMF of the larger inductor is what? Is B, which is 9.0 volts. And therefore a 3.5 inductor and a 4.5 millihenry inductor are connected in parallel. The equivalent inductance is what? It's A, which is 2.0 millihenry. So I need to know how to calculate inductors in parallel and inductors in series. So the answer is A. It's 2. I'm sure they did the parallel method because there's someone they cannot write here. Is 2. For Joe it was 9. I don't know how did they get that 9. A 3.5 milliamperes inductor and a 4.5 millihenry inductor are connected in parallel. When the total EMF of the combination is 16 volts, the rate of change of the current in the larger inductor is what? Is B. 3.6 times 10 to the power of 3 amperes per second. 3.6. I don't know this number. We've used it somewhere else. I don't know where, but we've used this number. 3.6 times 10 to the power of 3 amperes per second. So an inductor with inductance L and an inductor with inductance 2L are connected in parallel. So when the rate of change of the current in the larger inductor is 1200 amperes per second, the rate of change of the current in the smaller inductor is what? It's E, 2400. I like this number. The stored energy in an inductor is none of the above. The stored energy in an inductor is none of the above. So an inductance L and a resistance R are connected in series to an ideal battery. So a switch in the circuit is closed at time t is equals 0, at which time the current is 0. The energy stored in the inductor is a maximum. So E, a long time after the switch is closed. after switching by tswaletse. So an inductance L and a resistance L are connected in series to an ideal battery. So a switch in the circuit is closed at time 0. So at which time the current is 0, the rate of increase of the energy stored in the inductor is a maximum. Is a maximum when at the time t is equals to L over R in ln 2 after the switch is open. Hey, ln 2 by in 2. I'm sure ln 2. In each of the following operations, explain energy is expended. So the least percentage of returnable electrical energy will be yielded by what? By C. By sending current through a resistor. You take current and you pass it through a resistor. So a current of 10 amperes in a certain inductor, it results in a stored energy of 40 joules. So when the current is changed to 5 amperes in the opposite direction, the stored energy changes by what? By B, which is 30 joules. A 6,0 millihenry inductor is in a series circuit with a resistor and an ideal battery. So at the instant the current in the circuit is 5.0 amperes. So the energy stored in the inductor is what? Is B, which is 7.5 times 10 to the power of negative 2 joules. 7.5 times 10 to the power of negative 2 joules. 7.5 becomes regular. A 6,0 millihenry inductor is in a circuit. At the instant like the current is 5, and then the rate of change is 200 amperes per second. So the rate with which the energy stored in the inductor is increasing is what? SE. Obviously it's 6.0 watts, and therefore a 6,0 millihenry inductor and a 3,0 resistor are wired in series to a 12 volt ideal battery. A switch in a circuit is closed time 0, at which time the current is 0. A 2,0 millisecond later, the energy stored in the inductor is C, which is 1,9 times 10 to the power of negative 2 joules. One 1,9 times 10 to the power of negative 2 joules. And therefore here the quantity B squared over micro O has units of D, joules per meters cubed. Left with only 3. A 0,20 centimeter radius cylinder, 3 centimeter long, is wrapped with wire to form an inductor. So at the instant the magnetic field in the interior is 5,0 mt. So the energy stored in the field is about to be 3,8 times 10 to the power of negative 6 joules. So in the diagram, assume that all the magnetic field lines generated by coil 1 pass through coil 2. Coil 1 has 100 turns and coil 2 has 400 turns. Then E, it's none of the above. We have 2 turns here, we have this one and this one. Therefore, babulela ka EMF it over the same. Current ya ka mo feta ya ka mo ka bokae, EMF ya ka mo feta ya ka mo ka bokae, power ya ka mo feta ya ka mo ka bokae. But when you choose none of the above,